So my background is not as an economist or a stranded assets expert, but from the sciences. And I'm working with an organization called the Virgin Earth Challenge, which once upon a time used to be the largest innovation prize in the world until a few years ago, one-upped by Google. But the goal of the Virgin Earth Challenge is to look for ways of scalably and sustainably removing CO2 from the atmosphere and sequestering it securely, otherwise known as negative emissions technologies. So in my experience there, I've been contributing to a piece of work we've done with the Smith School, looking at what the implications of negative emissions technologies could be for stranded carbon assets in particular. And the inspiration for this work was this report. I won't go into it in detail because I'm sure you're all very familiar with it. The Action report by the Carbon Tracker in 2013, which effectively compared the carbon budgets we have available to maintain a good chance of staying within our climate targets, maintaining a stable climate, and the listed fossil fuel reserves on the market today, and concluded that one, the fossil fuel reserves was much bigger than the other, very simplistically, and therefore that should climate policy be put in place to regulate the total amount of emissions we can emit, then a large fraction of these reserves will not be able to be burnt in future, and therefore there is a risk of stranded carbon assets. For this, the purpose of this work, they also asked another very interesting question, which is about CCS. So if you are an owner of a coal plant like this, in principle, CCS is a way for you to decouple the fossil fuels you're burning from your emissions and from the carbon budget itself. So CCS is therefore potentially a way to extend the carbon budget faced by high emitters like coal plants. So the Carbon Tracker guys looked at the IEA CCS roadmap to outline an ambitious scenario for CCS deployment over the next 3.5 decades, and concluded that even with full investment in CCS, it extends the carbon budget for the 2-degree scenario by only 12 to 14%. In other words, carbon capture and storage does not fundamentally change the risk of stranded assets due to carbon constraints. But CCS is only one way of decoupling burning fossil fuels from the amount of carbon in the atmosphere. So in our piece of work, we asked a different question. What about CO2 capture from the air? Can this extend carbon budgets, what's known as negative emissions technologies? So first of all, how can we capture CO2 from the air? What are the different options? Well, it turns out there are quite a few. The first and most simplest is to use biology. Photosynthesis is amazing. It's the largest and oldest, one of the oldest capture pathways of CO2 on the planet. It has a good 3 billion years or so of R&D behind it. And biology, the biosphere, is naturally already capturing more than a quarter of the emissions we're putting into the atmosphere every year. So what are the ways we can enhance this sink? Well, of course there are. One of them is through better management and expansion of the forests that humans are managing. Forests are a very carbon-dense ecosystem. A typical forest like this, one hectare of forest like this will be storing well over 100 tons of carbon in biomass in soils, and will be sequestering carbon as it grows at a rate that is the same order as the average European's annual emissions. On top of that, planting forests is also quite low cost, and it can be associated with a lot of co-benefits, environmental co-benefits, especially associated with the water cycle and water quality. The other half of this is agricultural soil carbon. Here is agricultural soil carbon. There's a lot of it, it's a lovely black colour. The agricultural, or the soil carbon pool globally contains about 3 times as much carbon as is currently present in the atmosphere. And there are known ways to improve the way that plants and agricultural systems sequester carbon into the soil. There are cropping systems, there are grazing systems, we are aware of them, we know how to do them, and they are often also associated with co-benefits to fertility, to yield, and to resilience against climate events and fluctuations in water supply. Right, so that's biology. Basic biology, very well known. The limitations of biology are that you need a lot of land. There has a strong limitation on the land area that you have available to do these two in competition with other land uses. And on top of that, the carbon that you sequester is not truly isolated from the atmosphere. There's always the risk that when you plant your forest, 50 years later, a fire will run through, a drought will occur, an invasion of beetles will demolish it, or in fact it will be chopped down by road loggers. So there's always a risk that that carbon is released into the atmosphere. So the next logical step is, well, let's keep the photosynthesis of the CO2 capture part, but let's add a bit of kit to increase the security of storage. So there's a couple of ways of doing this. The most conceptually simple is pairing bioenergy technologies with carbon capture and storage. Basically, the simple flow is that the biomass feedstock captures CO2 as it grows. It's put into a bioenergy system, such as a power plant, which creates a co-product of electricity. Then the CO2 released from that is captured and stored underground or elsewhere. So the net result is a flow of carbon from the atmosphere into secure storage. A slightly different approach is the idea of biochar. Again, here, the process is the same. You have a biomass feedstock absorbing carbon from the atmosphere. But this time, rather than putting it into a power plant, you put it into this pyrolysis kiln. This bakes it at 200 degrees for a few hours in the absence of oxygen, and what you're left with, as well as some energy products, is effectively charcoal. The reason it's called biochar rather than charcoal is that you don't burn it, it's optimized to put into the soil where it improves soil quality. So if you're a farmer, you put biochar into your soil to improve your output, and that carbon biochar hopefully stays locked up for at least hundreds of years. So we got part of the way by adding technology. We've relaxed the constraint of permanence of storage, but we're still limited by biomass supply, and we're still limited by land use. So the last set of options cuts out the biological middleman entirely and says, well, can we use industrial processes, industrial chemistry, to capture CO2 from the atmosphere directly? Perhaps the most well-known example is something called direct air capture. I don't know if any of you have seen this before. This is an artist's impression of a real design of a system being worked on by a company in Calgary. Effectively, if you look closely, you'll see there's a lot of fans. What the fan's doing is drawing in air, passing it over a chemical liquid solvent, which strips out the CO2. The solvent is then passed off to a building over here off the screen, where it is heated, goes through a chemical process, the solvent is regenerated, and you're left with a 99% pure compressed stream of CO2 that you can do with as you want. One of the things, of course, you can do with it is to bury it underground, which would be a direct flow of negative emissions. Another option is a thing called ocean liming. The front end of this is effectively the front end of the cement industry. You're taking limestone, you're heating it, you're turning it into calcium oxide or lime, then you're diluting the lime and spreading it through the ocean, where it shifts the balance of carbonate chemistry in the ocean, also counteracting ocean acidification, and encourages more drawdown of CO2 into the seas. The thing to note here is that this technology produces a concentrated point source of CO2 during the calcination step, so you also need CCS for this to capture that CO2, for this to be a net life cycle negative process. This is just a quick slide to just say this is not something that exists entirely in an academic's fertile imagination. There are real companies out there that are, oh, that's an old picture, but then, real companies out there that are developing these technologies to near commercial stage. This is a bag of biochar mixed with compost that you can go online. If you're a farmer or a keen gardener, you can buy it. They have a process that's optimized to increase soil properties. This is the installation of one part of the regeneration facility for that artist's impression plant that you saw a few slides ago that they're doing in Calgary. So here's the broad landscape going from the biological options, which are more technically ready to go. You can do them now, but they are limited in terms of permanence and land availability, through to these slightly more advanced, slightly less known technological options that are less limited by the limitations on biological pathways, but are probably more expensive. They're not technologically as mature, and you need a lot more physical infrastructure and bits of kit to do them at large scale. So we looked at these six possibilities, and took a first step towards answering that question of what impact could these have on carbon budgets. We did nothing really sophisticated. It was quite a basic analysis. There was no consideration directly of the costs, no sophisticated consideration of the state of technological readiness, no big economic modelling or anything like that behind it. We were simply looking at what the fundamental limits were on these technologies and what kind of scale they could reach and when. So very briefly, these are the two, as you can see, very basic scenarios that we developed. Both of them are the same until 2050, just linear scale of technologies to an estimated 2050 potential. And then from 2050 to 2100, obviously the uncertainties when you have technology like these in that time period are mind-bogglingly large. So we put together a low scenario and a high scenario of different possible futures that these technologies could follow. And as you see later, perhaps it'd be better to call them a high scenario and an extreme, wildly ambitious scenario. But anyway, that's the basis for our analysis. So let's now look at results. First, 2050. This is from our analysis, the rough breakdown of where the potential for negative emissions to absorb carbon cumulatively by 2050. And again, don't look too closely at the numbers because the assumptions are very crude, but the overall message is quite robust, which is that most of the potential between now and 2050 to remove CO2 from the atmosphere is through biological methods, forests, agricultural, soil carbon, some deployment of biochar using agricultural residues. The reason is that, of course, these are the things we can do. Bioenergy and CCS, and then direct air capture and ocean liming in our model have a much, much lower cumulative capacity between now and 2050. The primary reason for that is because all of these are limited by CCS rollout. Each one requires carbon capture and storage and either geological sequestration or otherwise to have net life cycle removal of CO2. Now let's look at the longer picture. The scale of that bar on the left is the same as the bar from the previous slide. So obviously the first thing to notice is that once you get into the 2050 to 2100 period, the technically feasible, the technical potential, I would say feasible, for these technologies to sequester CO2 is enormous. It's on the order of hundreds of billions of tons of CO2 cumulatively, up to over 1,000 billion tons of CO2 cumulatively. This is a number that is on the same order of magnitude as the total carbon budget the world faces between now and 2100. The second thing to see from this picture is that once you get past 2050, these tech options, these big bits of kit, have a much bigger role to play. You're suddenly dealing with, so say you have a much more developed CCS infrastructure, perhaps you have a high carbon price, your technologies are more developed. In theory, these things are much less limited by any fundamental constraints than the biological pathways. Biological pathways, in contrast, dwindle into a much less significant role on the long term. But before we get too excited, there are some caveats. This is just a low scenario, and you can see that even to achieve this relatively modest sequestration potential by 2100, you need new industries to remove carbon that are at least as large as some of the largest industries we have on the planet today. So through ocean liming, to achieve that little blue wedge, you need to be producing lime and spreading it in the ocean at the same time, at the same scale as today's cement industry is doing. For direct air capture, you need to be putting as much compressed CO2 back underground from those fan contractions as today we are currently taking oil out of the ground. Bioenergy and CCS, again you have another oil industry or more's worth of geological sequestration required to make this a reality. Plus you also need nearly a third of today's cropland area growing energy crops. And to produce biochar at that kind of scale, you need to be capturing most of the crop residues produced and agricultural residues produced today and feeding them into an industry which grows to 20 times the size of today's charcoal industry by 2050. So those are big, big industries. So the upshot of this particular slide is this is not an easy way out. There is no magical technology that is going to suddenly appear in 2050, you build a few plants and it deals with your CO2 problem. There's no way this is going to be easier or cheaper than mitigating emissions sensibly in the first place. So just a few broad implications for asset stranding. This is not my area of expertise, but I have four main points, I think. One is, if you're looking in the near term, the next 30 years or so, there is no way that any negative emissions sector could develop that could significantly change the risk of asset stranding due to carbon budgets, even if you push really hard on the order of 10% expansion. The second is that even on the whole century timescale, 100 years, reaching a scale of an industry that would have a real impact on carbon budgets is possible, but enormously difficult and very uncertain. So you'd be mad, technical term, to assume that the availability of these technologies, even at large scale in the future, is going to enable you to keep burning fossil fuels today and then recapture those emissions at low cost. Third point is that these things cost money. Someone's going to have to pay for it, even if we do it at large scale. And it seems perfectly reasonable to me that should the world decide to do this and remove CO2 at large scale, the person they will ask to pay for it will be the organizations and industries that put that CO2 up into the air in the first place. The polluter pays principle applies, and it means that this is unlikely to be, even with this at large scale, business as usual for carbon intensive sectors is not an option. The flip side of that is that a potentially valuable role as far as stranded assets go for these technologies is in potentially offsetting or neutralizing emissions that are difficult to get at in any other way. So those industries that have no economically viable alternatives for getting their emissions to zero in the near future could look at partnering with these technologies and developing these technologies. So shipping, aviation, perhaps the agricultural sector, some industrial sectors could be paired with these technologies to deal and clean up the emissions that they are unavoidably going to make. So a few key conclusions that I want you to take away with you. First is that these technologies are real and they're being developed and they have a real tangible material potential to help the global economy decarbonize and remain within the planetary carbon budget. It would be a mistake not to give these technologies more investment, more policy support, more research than we currently are doing. On the other hand, negative emissions will never be available at the scale and the cost that we need to actually offset a large-scale fossil-based sector operating in parallel with it. So you'd also be foolish to assume that business as usual can continue for any particular reason. Last and most importantly for this conference, it's very unlikely that development of negative emissions technologies in all their forms will fundamentally alter the carbon budgets that owners of carbon-intensive assets are facing due to strict climate regulation in the short or long term. And thank you very much. And
well, that was ambitious. Covered a lot.
Right, sorry.
Not too fast. One from Rob. Let me just look around the room. Boom, boom, back row, here. Okay. 6 questions. We got 5 minutes, so try to make your questions and your answers as brief as you can.
Very balanced talk. There is a factor of probably a 2 that you haven't included, which makes these negative emission technologies less effective. That is that when you take carbon dioxide out of the atmosphere, it goes back into the atmosphere from the ocean and probably from forests, because it reverses what's going on right now. We don't have 100% of what we put into the atmosphere stay there, but rather more like half.
Yeah.
So when you had a graph with the tons of carbon on one side and ppm on the other on the 2 vertical axes, and there was a 1-for-1. You didn't allow for that, which is a big deal because it means it would be half as effective with these technologies as we wish we could.
Sure, yeah, that's a very, very good point. You can't translate removal of CO2 straight into a parts per million effect on the atmosphere, because certainly the ocean and quite possibly the biosphere will start regassing CO2. That's a very, very fair point. I suppose in terms of carbon emission and sequestration, on that basis there is still a 1-to-1 balance. Perhaps this is debatable actually, I'm not sure, but it seems to me that there's still a 1-to-1 balance between emitting a ton of CO2 and sequestering again a ton of CO2. I think that's what the carbon budget says.
Thank you for the permanence question. So, yes.
Thank you. Based on the pilots, Hamish Stewart from the Asset Owners Disclosure Project, based on the existing pilots in Australia and Canada, my question is that the insurance industry won't touch this kind of technology with a 10-foot pole because of future emissions and then leakage. It cannot be insured. And so how do you overcome that as a barrier to the business model?
That's a very tough one. I won't argue, especially with something like soil sequestration. I mean, forestry and agricultural methods have failed to penetrate into the EU emissions trading scheme. I think for precisely this reason, you'll never be able to quantify and guarantee the sequestration in the same way that you can an avoided emission. So yeah, I mean, part of the answer is that it doesn't all depend on carbon markets for these technologies. That it's not all going to be a matter of paying per ton of CO2. That's one business model, but it's not the only one. And like, you know, I think the other part will have to be, as you're developing for bioenergy, as you're developing for fossil carbon capture and storage, policymakers will need to develop protocols in order to account for those risks, in order for these things to participate sensibly in carbon markets.
Indeed, a broad topic you've engaged us in, and thus we have time only for one more question, I'm sorry to say, and so brief, as well as a brief response, and then Guy, you'll be around at lunchtime?
Yeah, absolutely.
All right, terrific. So, I believe there's...
Guy, are there offsetting effects of other pollutants, emissions like NOx, mercury, and whatnot that are going to have health ramifications with the magnitude of the negative emissions collection of CO2?
There may well be. So in the Virgin Earth Challenge, at least, one of our criteria for selecting a winner, and honestly one of the reasons we don't quite have a winner yet, is they have to be able to show minimal to positive environmental and social impacts, including health, of the technology. So the idea is, can you demonstrate that you are developing a technology that, if scaled to a level where it's removing hundreds of millions of tons of CO2, will not cause some, will not be emitting some other pollutions or causing some other environmental or health impacts. Certainly, that's one of the core objectives of certainly the air capture side of things. As far as biomass and land availability goes, I mean, that's a kind of a whole other topic and another discussion of what land use activities at this kind of scale will involve and use. So of course that's one of the primary limitations on getting to anywhere like this kind of scale, that you have to deal with the conflicts and side effects that your ambitious changes to land use are going to drive worldwide.
All right. It sounds like you've taken the Virgin Earth Challenge yourself by taking on all these negative emissions technologies. All right, so let's thank Guy.